Hello everyone, welcome to this video. In this video, we'll be looking at examples of group homomorphism. So in the first example, we have R star to be the group of non-zero real numbers under multiplication, right? So the determinant mapping from A to determinant A is a homomorphism, right, where our group is this general linear group of order 2 consisting of all 2 cross 2 real matrices, right, and this R star is a non-zero group of non-zero real numbers under multiplication. So you see, this is some matrix and this is some determinant which is a real number. Now we say this mapping is homomorphism. How? That is why we are defining it from GL2 comma R to R star, and we are defining it to be like this, right? It is the determinant of A. Now using this mapping here, we have to prove that phi of AB is equals to phi of A into phi of B. Now this is normal multiplication of two numbers, and what is this? This is the multiplication, matrix multiplication, right? Capital A and capital B, they are two different matrices taken from GL2 comma R, right? So obviously they are non-zero, their determinant is non-zero. Okay, so if we take the left hand side here, phi of AB, this is determinant of AB, and by the properties of determinant you can write it like this: determinant of A into the determinant of B. Similarly, the right hand side, phi of A into phi of B is determinant of A, determinant of B. So both of them, they are equal to each other, hence you have a homomorphism here in this particular case, right? In the second example, let's consider the mapping from R star to R star. Again, this is the set of real numbers which does not contain 0 within it, right? We define it to be like this: phi of x is equals to mod of x. So this mapping here is a homomorphism. So here in this case, we have to prove phi of xy is equals to phi of x, phi of y. Why? Because here also the operation is multiplication, here also the operation is multiplication, right, in this particular group. So let's take the left hand side, phi of xy, which would be the mod of xy, right? According to the properties of mod, this is equal to the mod of x into the mod of y, right? The same thing. Now what is mod of x? It is phi of x. The mod of y, it is phi of y, and this becomes your right hand side. Hence we have a homomorphism in this case. As for the third example, let's consider Rx to be the group of all polynomials with real coefficients under addition. Right, now we define our mapping from the first of all, let's say phi is our homomorphism, and we are taking this from Rx to Rx. So that means we are taking it from the group of all real polynomials to the set of all, group of all real polynomials, right? And we are defining it to be like that. Here we have polynomial. So polynomial, let's take it to be f. This would give you the derivative of this polynomial, right? This f bar, or some people call it f dash, some people call it f prime. Both are correct. And here this denotes the derivative of f. So that means this mapping f to f dash is a homomorphism from this group Rx to itself, correct? Okay, moving further on to our next example, we have the mapping phi from this group of integers to the group of integers modulo n, right? Here what is the operation? The operation is usual addition, and here what is the operation? The operation is addition modulo n, right? So here this is also an homomorphism when we define it to be when you take the number m and when you take its mod n. This is also a homomorphism, right? This we have, this kind of homomorphism we have proved in our previous video, right? Okay, moving further, let's take example 5 here. In this case, we say the mapping which is defined from phi from the set the group of all non-zero real numbers to itself, right, such that phi of x is equals to x square. This is a homomorphism, right? How? When you take phi of xy, by the definition here, it is equal to the square of the number, so it is equal to the square of xy. So you can write it as x square y square. So you can write x square as phi of x, y square as phi of phi, and this is what we wanted to prove here. Hence this is a homomorphism, right? Moving further, let's see next example. In this example, we again take the same mapping, but now our group is different. We are taking this mapping from the set of real numbers to the set of real numbers, right? And where the group operation is addition and not multiplication. So here in this case, we wanted to prove that phi of x plus y is equals to phi of x plus phi of y, correct? So here for this, let's take the left hand side first. So by the definition, phi of some member is its square, so it would be the square of this number x plus y. So when you open up the square, you get this expression, x square plus 2xy plus y square. And on the right hand side, you have phi of x plus phi of y. When you open up this phi of x, you would have x square. When you open up phi of y, by definition it would be y square. So you see, both of them, they are not equal to each other. Hence, we do not have a homomorphism in this case. This does not form a homomorphism under addition, correct? As for the next example, all of us might have studied about linear algebra, so we also have studied about linear transformations there. So these are also the mappings, right, which preserve order, so they form group homomorphism. And if you take the mapping to be invertible mapping, so invertible mapping, if you remember, is 1-1 mapping onto mapping, and moreover, because it is a linear transformation, it is also order or operation preserving, right? Now it has all the three properties, hence this, now the invertible linear transformation also forms an isomorphism, group isomorphism, right? So you see how we have connected this abstract algebra to the linear algebra. While when you define any homomorphism, which is quite simple, one thing should be kept in mind, that you should check that whether it is a function or not. This thing should be checked. For example, let's define this map phi from this group, which is the quotient group or the factor group of z, with this subgroup generated by 3 to z6, which is the group of integers modulo 6, and we define it to be like this: phi of the element here, you know, are of cosets type, right? So it would be written as some x taken from integers, and you have this as your subgroup, so the element would be like this, right? So you will apply phi onto this element and you would get 3x. This is how we define it. Now this definition we say is a homomorphism, right? Why? Because phi of, we wanted to prove that phi of x plus y is equals to phi of x plus phi of y, right? So what is phi of x plus y? By the definition, because our domain is this quotient set, so our element would also be of this form, x plus y plus our subgroup, right? So when you apply the definition here, you will get 3 times of this element x plus y, right? You can open up the brackets, you have 3x plus 3y. Now you can express this 3x as 3x plus this factor, this subgroup x, right, in terms of coset, and you can define this 3y as 3y plus this coset. Hence you have defined the first member as phi of 3 plus I have written it wrong. You can define it like this: x plus the subgroup generated by 3 and y plus the subgroup generated by 3, correct? Now we say this is not a function. Why? Because for a function, if we take the if we take two elements as equal to each other, right, then their mappings should also be equal to each other, right? However, this should imply this thing. However, in this case, we take two elements as equal. You know, in factor group, the element 0 plus subgroup generated by 3 is equal to 3 plus subgroup generated by 3, right? This thing you know. However, the function phi of 0 and phi of 3, they are not equal to each other. Why? Because what is phi of 0? It is 3 into 0, which is 0. 0 mod 6 is 0 only. And what is 3 into 3? It is 9. 9 mod 6 is equals to how much? 3. So 0 is not equal to 3 when we are in this group Z6, right? So this is not a function, however it is order preserving. So we cannot use this to define our homomorphism. So I hope you understood these examples well. Well, that is it for this video. Thank you for watching.